morning, listeners. Good morning, students, parents, teachers, and all lovers of knowledge. This is Oxygen FM 96.9, where the station that informs, the station that inspires, and the station that ignites. Yeah, I welcome you to another exciting edition of School on Here Physics, your favorite program where physics comes alive and beyond the classroom. I'm your regular host, Kenny BADMUS. Today, we're going to make physics as simple as ABC, practical and interesting. Yet on behalf, before that, I want to say to students, I want to call your attention that we are where we are today and the lesson has started. Please come around and let's us, reach out and have some things to learn today. On behalf of the management and the production crew of Oxygen FM, situated on the Knowledge Hub 121-123 Obafemi Awolowo Way, Okeado, Ibadan, I want to welcome you all to another exciting and transformative edition of School on Here Physics on O2 FM, that's Oxygen FM 96.9, where our guiding philosophy remains firmly rooted in education and enlightenment, and it illuminates the mind one lesson after another. I remain your host. Like I said, I'm Kenny BADMUS. I will pilot you and I'll be guiding you through today's exciting journey into the world of science. Behind the scenes that makes this edition and the delivery of this academic work meaningful is my producer, Mr. Olufemi Timothy Ogunyejo, which is vibrantly committed to this educational excellence. I'm my studio engineer and ultimately the head of station, Mrs. Tokumbo Ishola. Thank you for being there for us. Yeah. Today, on the first segment, we're going to read our wisdom capsule as usual. And today's topic is still efficiency of machines. Like last week, we discussed efficiency of machine. We discussed what is a machine. We discussed the common applications of machines. What are the capabilities of machines? The four relevant formulas that are related to efficiency. Then we discussed the mechanical accuracy. We discussed the velocity ratio and how we can model the two together to get efficiency. So then today again, there are quite a number of salient, very important concepts that were not discussed last week due to time. So today we're going to add up to that. We're going to have a review of what I've explained earlier. Then we now have a fresh presentation in addition to what we've discussed, what I've laid down, all those few things, all the concepts of mechanical accuracy, velocity ratio, and all the rest. So before we start that, I want to go to the wisdom capsule for today. So the wisdom capsule for today, I still want to repeat that it's still about the history and the life of a remarkable English physicist whose discoveries helped the world understand one of the most important ideas in physics, the relationship between energy, work, and heat. His name remains the same, James Prescott Joule. This is JP Joule. James Prescott Joule, was born on 24th December 1818 in Salford, England, and he died 18 October in the year 1889. So that's after he lived for 71 useful years on Earth. Joule was a physicist who made important contributions to the study of energy and heat. So he's best known for demonstrating the relationship between mechanical work, heat, and energy. His experiments helped establish the principles that energy can be transformed from one form to another. So in recognition of this great contribution to physics, the SI unit of energy and work, which is the joule, which is symbolized by J, was named after James Prescott Joule. So as students and lovers of knowledge, I want us to think or imagine you that, putting up great deal of work that impacts the life meaningfully to point of you being remembered, or your name being written in the fame, being noted in the world of science, particularly physics, as a course of study now. So students should think about a moment and imagine making such a meaningful contribution, very important, very salient contribution to science, that your name is being part of language of physics used by students and scientists all over the world. So I want to move on to the main work, that's efficiency of machine. That is the main topic of today, with emphasis on lever, simple machine and lever system. But we want to make a review of what we did last week. Like I have said, that what efficiency of machine, what are we talking about machine? What are the common applications of machine that we can see around us? And what will come to mind when we think of physics, and when we think of machines, and when we think of a car, we think of a generator, we think of bicycle, we think of wheelbarrows, cranes, pulleys, and even simple bottle openers, scissors, and all this. So these are machines in their own right. You may think of a opener, how can we call this a machine? You may think of a scissors, how can we call this a machine? These are simple machines, and it is the combination of simple machines that make up bigger machines. So all of these can help us to understand today's lesson. But there's a big question I want to repeat, that does every machine give back exactly what they put in? It is obviously no. Obviously, no machine gives back what is put in. It is not give out. So there are associated losses when machines operate. So if you put, for example, if we put 100 units of energy into a machine, we always get 100 units of useful output. But definitely no, we cannot. It can only be imagined. So why? And this brings us the main topic of efficiency of machine. So it is the output that determines the efficiency of a machine. So students, wherever we are, sit up straight and get your exercise book ready and learn something. So welcome back to the main topic, that what is a machine? So let us begin with the basics. This is a recap, this is a repeat, and students be aware that we may not be able to repeat over and over, but notwithstanding, we're still going to repeat very useful, parts to make us understand and make this lesson very, very interesting. So what can machine do for us? What is the capability of machine? So machine often help us to multiply force. So it helps multiply force, it helps change direction of force, it increases the speed, it transfers force from one point to another. It makes work more efficient. That is even the basic definition, the concise or simplest definition of machine, that is a device that helps us to perform work more easily. So that is one of the characteristics. What are the things it can do for us? That machines make work more convenient. For instance, now let's think about a wheelbarrow. If you want to move a more heavier or heavy load, carrying it directly may be difficult. But when you put the load inside a wheelbarrow, the wheelbarrow will help you to move it easily. So let's also think about a pulley. If you want to raise a heavy load vertically, raise it up, it it's only the pulling that can help you change direction. That's the direction maybe horizontal before, so it has to bring it to a central point where it is lifted up vertically. So that is how it changes direction. Those are the capabilities. So also think about a bicycle. So it's in the pedal. When you apply your force to the pedal, the machine will help you transfer your effort to the wheel to produce motion. So machines make work easier. But there is something also more important for us to understand, that it's more of a question, that does machine create energy? So does machine create energy? So a machine does not create energy. A machine only help to use energy we supply in a more convenient and useful way. So machines does not create energy. It only helps to use the energy supplied in a more convenient and useful way. So this is where the concept of efficiency comes in. So let's ask ourselves, what does efficiency mean? How are you efficient at your tasks? So in simple language, efficiency tells us how well a machine converts energy or work supplied to its useful output. So efficiency tells us how well a machine converts the energy or work supplied to it into useful energy. So a machine is said to be efficient when a large proportion of the input energy becomes useful energy. So I want to repeat that a machine is said to be efficient when a large proportion of the input energy becomes useful energy. So like we said earlier, that no real machine is 100% efficient, because some energy is lost. Some energy is lost one way or the other. But where does the energy go? The lost energy, where do they go? So some of these energies lost through one, friction. Some of this energy are lost through heat. Some of them are lost through sound. Some of them lost through vibration. Some of them lost through air resistance. Some of them lost through deformation of machine parts. Some of them lost through misalignment of parts or machine parts. So like for example now, when you ride a bicycle, not all the energy you provide through the pedaling is converted into the forward motion. At least there must be a moment through which you gather momentum. So that is to gather sufficient energy to move the machine forward. So some energy is lost there at that point through friction in the chain, gears, and bearings. So some are lost through heat. Some are lost through the production of sound. So the machine cannot convert all the energy into useful output. So that's why we say real machines have efficiencies less than 100%. Welcome back once again. Let's make it a little bit practical to make it clearly and clearer and understandable. So now let's discuss this importance of efficiency. Why can't most real machines achieve 100%? We have said it that there are losses due to friction, there are losses due to sound, there are losses due to vibration, losses due to air resistance. And to make it a bit practical, the major reason energy is lost, and one of the major reasons is the energy lost through friction. So how do we see that? How can we understand that? friction will occur when two surfaces move together. So like at the last class, I think I said something about a milling machine. Even in some milling machines used for food, and you think of milling machines too that are used in sawmill. So frictions occur when two surfaces move against each other because the fineness, the smoothness of each of these surfaces are different. So they have to bring about an alignment, to make sure that the surfaces are as smooth as possible. One will condition the other to achieve to attain its own fineness so that they can move together. That's what makes milling. Like pepper, seeds like beans, rice, maize, and all that. So the machines condition all these goods to its own fineness to achieve milling, pulverizing, or whatever we call it. So also in that process, heat is developed. So the heat energy represents energy that is no longer available as useful energy, as useful output. It's being dissipated out. That's why when you go to where practical work are being done, like the milling industry, whether sawmill or food processing industry, the working environment, environments are often high in temperature. This is due to energy dissipation from these machines, which are useless. They are not useful. They are not the useful part of output that we want. So another source is the loss due to sound. When a machine operates, you hear noise. And this noise, is measured in decibel. And scientists have done incredible work over time to know the maximum quantity or the number of decibel with which human hearing can afford. So in production environment, you will always know that there are heat and noise associated. So these are where sounds are lost, where energies are lost due to sound, noise, and all that. So another one is the vibration. Some machines vibrate when they operate. So at the energy transfer into those vibrations are not the useful energy that we want. Some also are lost through air resistance. Like I can say this, that when you are here, let's take an aircraft for example. They do not on the high altitude where aircrafts move, where it operates, it does not have tar road. It is the air resistance that it goes against, it moves against. So when an aircraft wants to speed up, it has to increase its speed to move against the air tide, because the tidal waves that's going against this aeroplane is very massive. It's unlike the air that we have on the ground. So let's know that, students, please. So invariably, lost energy is observed as a result of that, because it has to buckle up to increase its energy. When increase that energy sufficiently, it has to increase it to a point at which it boats away from that air resistance. So all these contribute to energy losses. So when we say a machine is 100% efficient, how does it mean? And it means that 20% of the energy has disappeared. However, we should understand that energy can neither be created nor destroyed. Invariably, The energy that disappears is being transferred. That's why we talk about heat. We talk about sound, noise, and vibration. Yeah, welcome back. Thank you for being there. Now, we want to also discuss that how we improve machine efficiency. How do we improve machine efficiency? Because we have to be concerned. That is the source of concern. Why is it a source of concern? It's a source of concern because we have to increase the efficiency as much as possible. You cannot afford, if you leave a machine to itself, it can give you 40% efficiency, which is not useful to us. You want to maximize, you want to optimize its use. That's why you rent it. That's why you procure it. So scientists have done a lot to improve machine efficiency. One of the things that they do to improve efficiency is lubrication. So when we apply oil, grease to moving parts or contacts, this reduces the friction between surfaces. So lubrication is one of the ways by which we improve machine efficiency. Number 2 is proper maintenance. Proper maintenance. Number 3 is good design from the engineer. So engineers design machines to reduce unnecessary energy losses. So maximally, that's what they call optimization. So we want to achieve maximum results at lower variables or inputs. So all the accessories, all the components gathered together, how do we combine them? How do we put them together to get our desirable result that will give us maximum efficiency? So also using suitable material, using suitable materials, appropriate materials at the right place. So at the right place, that brings us to proper alignment of moving parts. So component parts must not often be improvised. Okay, let's use this. Okay, it's not available. However, we know certain times machine parts are not readily available. That is part of planning. So for you to rent a machine, for you to order a machine, for you to buy a machine, you have to consider what are the useful parts that often breaks down. That is often breaks down often. So you have to get them in place. Even those that may break down long time, you have to consider. Those are factors to factor in, to put in place. So when the machine is well maintained, so usually it's more efficient. When the machine is well maintained, the efficiency is higher. However, if it is poorly maintained, the efficiency is definitely lower. So we now move to the concept of efficiency / mechanical advantage and velocity ratio. So what is mechanical advantage? What is velocity ratio as regards efficiency? So mechanical advantage tells us about the relationship between load and effort. The mechanical advantage is a relationship between load and effort. So while the velocity ratio tells us about the relationship between the distance moved by effort and the distance moved by load. So you have to understand the two. One borders, the mechanical advantage is bordered purely on how much is the load, how much is the effort. So while the velocity ratio is a concern of the distance with which the load is moved, with the distance at which the effort is applied. So efficiency now tells us how effectively the machine converts the input work into useful output. So relationship between efficiency, mechanical advantage, and velocity ratio. So that brings us to the simple definition, or let's say the mathematical representation of efficiency in terms of mechanical advantage and velocity ratio. Efficiency equals to mechanical advantage divided by velocity ratio times 100%. That is, efficiency equals to mechanical advantage over velocity ratio times 100%. Efficiency equals to MA over VR times 100%. So let's take an example. So suppose we have a mechanical advantage of a machine to be 4, while the velocity ratio is 5. So the efficiency, straightforward, is MA over VR times 100%. What is our MA? That's mechanical advantage. It is 4. What is our VR? That is 5, velocity ratio. So MA over VR is 4 over 5 times 100%. So if you cut it down, it will give us 80%. So which is very, very absolutely good for a machine to have an efficiency of 80%. So but for a real machine, let us know it is a warning that mechanical advantage is usually less than velocity ratio. For students at home, note that this is a practical questions that was often asked, maybe WAEC, be it WAEC, NECO, JAM, or whatever. So they will ask you, does the mechanical advantage greater than MR? Say true or false. MA less than VR. MA greater than VR. True or false. So MA is less than VR. Please note that. So because of the fact that some energy is lost, that is why MA is less than VR. So no real machine is perfectly efficient. Now to the addendum. That is the addition to our lesson of today. So the addition to the lesson of today is on lever system. So lever system and simple machines as it relates to lever system. So what is a lever? What is a lever? What is a lever? So a lever is a machine consisting of a rigid bar. Rotates about a fixed point that's usually called fulcrum, and it helps us to lift up or move heavy loads with less effort. So a fulcrum consists of a rigid bar, rigid in the sense that it has to be strong enough to have the capacity to carry a load at an extension of length. So that's where the velocity ratio comes in. So where do we find those activities? It's usually found in our schools, where you see children, some sitting down on this edge of a rigid bar, while some sit down on the other hand. So whose weight are different from each other. So, and they try to dangle over the bar over and over, having their fun. So that is a simple common example of a lever system. So a lever, by definition again, is a simple machine that consists of a rigid bar that rotates about a fixed point called the fulcrum. So the word fixed point, fulcrum, is very, very important. That is the hinges with which it moves, it rotates. It dangles, it rotates. So a simple lever is a simple machine consisting of a rigid bar that rotates about a fixed point called fulcrum. It helps to lift or move heavy objects with less effort. So what are the major parts of a lever? So from that practical example, you see somebody sitting down at two ends with the rigid bar pivoted or hinged at a fixed point with a fulcrum. So what are the major parts of a lever? So in a lever system, you have a fixed pivot point. You can call it pivot, you can call it pivot, P-I-V-O-T. That is what separates the two ends of the load and the effort. So that's fulcrum F. So another part is the effort E. Another part is effort E, while the third part is load L. So E, effort, is a force applied to the lever, and the load is an object or resistance being moved. So the load is an object or resistance being moved, even be it human being, anything resistive that you are trying to drag, move, or position to a higher height. So the principle of a lever works according to the principle of moments. So, and the principle of moment is clockwise movement equals to anti-clockwise movement. So, like I said, that on a rigid plane where we have two children sitting down at two ends. So the other one, the one with the load, the other one with the effort, designated load, designated effort at different distance to the pivot. So the distance to the pivot are not the same. It is not inked at the same, at the center. So the distance from the fulcrum to the effort is different. From distance to the fulcrum, from the fulcrum to the load is different. So, like I said, that the principle of movement is the basis. Let's note, students at home, please note that a lever system works on the principle of moments, where clockwise movement equals to anti-clockwise movement. Mathematically, I want to repeat that the principle of lever works according to the principle of moment, where clockwise movement equals to anti-clockwise movement. Now, mathematically, effort times effort arm, that is the distance, equals to load times load arm, that is its distance, associated distance. So that is the principle of movement, the clockwise movement and the anti-clockwise movement. So classes of lever is very, 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 very important for us to understand. That's why we are bringing it today again. So what are the classes of lever? We have a first class lever, we have second class lever, we have third class lever. So, and it will take us back to mechanical advantage, velocity ratio, and efficiency, and everyday application. So before the close of time. Now, at the first class lever system, arrangement of the fulcrum. Please note, students at home, that first class lever system, in the first class lever system, arrangement of fulcrum is between effort and load. Arrangement is between the fulcrum and fulcrum is between effort and load. The fulcrum or the pivot is always in between effort and load. So first class lever system, in its arrangement, the fulcrum is always between load and effort. That's to say, on a plain bar, rigid plain bar, you have effort on this side, on the first side, and load on the second side. At the center, which may not definitely be at 50% distance, equidistance. But at distance, the fulcrum or the pivot is positioned. So examples of a first class lever. Students, please write it down. Example of a first class lever system are seesaw, scissors, crowbar, pliers. So example, I want to say again for the first class lever system: seesaw, scissors, crowbar, and pliers. Please note that examples of first class lever system are seesaw, S-E-E-S-A-W. That's seesaw. So next is scissors, which is S-C-S-S-O-R-S. So third is the crowbar, and the fourth one is the plier. So this are the second class lever system. Second class lever system, the load is between fulcrum and effort. Please try to understand the arrangement. The load now comes between the fulcrum and the effort. At the first class, the fulcrum is between. Fulcrum is the same as pivot. So that fulcrum or pivot is between at the first class lever system. The fulcrum or the pivot is between the effort and the load. This time at the second class, load is between fulcrum and effort. Please note that at the second class lever system, load is positioned between the fulcrum, that is the pivot, and the effort. We have an example, which is oftentimes every day in our everyday life. We see examples like wheelbarrow, bottle opener, and nut crackers. So wheelbarrows, bottle openers, nut crackers. These are typical concepts that's usually examined by examiners, examined to students by examiners at be it WAEC, be it NECO, be it JAMB, So you always find it. Examples of first class lever system, example of second class lever system. So example of second class lever system now, I say, is wheelbarrow, bottle opener, nut cracker. So and the second class lever system, mechanical advantage is usually greater than 1. Please write it down. Please write it down and memorize that at second class lever system, mechanical advantage is usually greater than 1. It's usually greater than 1. Now to the third class lever system. The third class lever system, this time effort is between fulcrum and load. Effort is between the fulcrum and load. The effort is between the pivot and the load. Remember that first class lever system, the fulcrum, which is the pivot, is between load and effort. First class lever system, the pivot or the fulcrum is between load and effort. Remember, the examples. Second class lever system, the load is standing in between the fulcrum, which is the pivot, and the effort. So the load is in between, positioned between the fulcrum and the effort. This time at the third class lever system, the effort is positioned in between fulcrum, which is the pivot, and the load. So third class lever system, the effort is between the fulcrum, which is the pivot, and the load. Please note it. Please note it for examination purposes. So examples are woman forearm. Everybody has his forearm. Please, students at home, stretch your hand like this. Stretch it, as if you want to gather muscle. So that system there, it's an example of a third class lever system where your effort is between the fulcrum and its load. So second one is the fishing rod. So I'm not saying fishing pond, it's fishing rod. So the third one is tweezer. third example is tweezer. And the fourth example is the broom. The broom that we use at home. The broom that everybody is used to in our homes, various homes. It has an advantage. Third class lever system has an advantage. The advantage it has is the fact that it increases speed and distance rather than force. The speed and distance are increased rather than force. That's an example. That's an opportunity. You don't need to increase your force. When you increase your force, you think about energy, you think about work. But this time, with less work, with less energy, you achieve a result. Except that there's an extension in distance, which is a function of speed. So your increased advantage that third class lever system has is the fact that it increases speed and distance rather than force. Please, student at home, note that. Now you come back to the principle of mechanical advantage, MA. Mechanical advantage tell us how much a machine multiplies force. We say the advantage of machine is that it multiplies force, it changes direction of force, and all that. So what is the formula again? The formula again is MA is load over effort. MA, which is the mechanical advantage, is load over effort. For an ideal lever system, MA equals to effort arm over load arm. Now, look at it critically. When MA equals load over effort, MA, which is mechanical advantage, is load over effort. But for an ideal lever, the MA is effort arm. You can now see that effort is transposed. Effort is the denominator before. It now comes up. That's why it's transposed. The word transposed. It has an opportunity. So they move it up. So it now becomes effort arm, not the real effort. The effort arm, that is the distance, effort arm over load arm. MA, mechanical advantage, is effort arm divided by load arm. Why in standard formula we have MA, mechanical advantage, as load divided by effort. So efficiency of a lever this time now is the same as we have done before. That mechanical advantage over velocity ratio times 100%. So we remember that no real machine is 100% efficient because some energy is lost due to friction. Now let's remind ourselves again about everyday applications. So in everyday applications that we are used to, we can see lifting of heavy stones with a crowbar. We can see carrying loads with a wheelbarrow. We can see cutting materials with scissors. We can see opening bottles with a bottle opener, not with teeth this time. Students, I know you are still to want to open mineral with your teeth. Please don't do that again. It can break your teeth. So everyday applications. The last one that we can see here is using pliers to grip objects. Using plier to grip objects. So now to worked examples. So I want to give you one. So to the worked example, I have a lever system lifts a 120 Newton load using an effort of 40 Newton. And a lever system lifts a 120 Newton load using an effort of 40 Newton. Find the mechanical advantage. Find the mechanical advantage. And we remember that mechanical advantage is load divided by effort. So what is our load this time? The load is 120 Newton. 120 Newton, that is the one up. And the one down is 40 Newton. So let's have a cut. So we can see that we have mechanical advantage to be 3. So mechanical advantage is 3 in this case. So students at home, for classwork, for when you sit down, you can think about all this, that you can identify classes of lever for each of the following. Try at your convenient hour to identify classes of lever for scissors, for wheelbarrow, for woman forearm, for bottle openers, for seesaws, and whatever you see around you. Try to look at it critically and think of what is the lever system associated. So we've discussed that earlier. Please try to remember what are the classes of lever, the first class lever, the examples. The example of first class lever system, which is a seesaw, scissors, crowbar, pliers. Second class lever system has examples as wheelbarrow, bottle opener, nut cracker. The third class lever system has a forearm as an example, the fishing rod, the tweezer, and the broom. So from that, I want to ask, before I open the studio line, that what is the lever system associated with these five? The scissors, the wheelbarrow, the forearm, the bottle opener, the seesaw. Please think about that. So so student line is already open. 0704700493969 rather. 07047003969. 07047002969. 07047002969. 07047004969. 07047004969. Open. Okay. Hello.
Hello, sir.
Hello. What's the name?
My name is Blessing Wawulu.
Okay, Blessing Wawulu from Oduola. How are you today?
I'm fine, sir.
Thank you. Yeah. What is the lever system of scissors?
First class.
Okay. Correct. What's the lever system for the wheelbarrow?
Second class.
Okay. What's the lever system for woman forearm? Third class. Okay. What's the lever system for bottle opener?
Second class.
Are you sure?
Yes.
Oh, correct. So what's the lever system for broom?
First class.
What?
Fourth class.
No. It's not fourth class. There's no fourth class. First, second.
No, third class.
Third class.
class.
Third class. So you are very correct. Thank you for that. Hello?
Hello, sir.
You're still there. So define mechanical advantage. Define mechanical advantage in the
Mechanical advantage is the relationship between the load and effort.
Okay, that's a description. Good. What is the formula now?
A mechanical advantage is equal to load over effort.
Okay, that's one. Second, for an ideal lever system.
Yeah?
For an ideal lever system, what's the mechanical advantage in an ideal lever system? Ideal lever system, what's the mechanical advantage?
Load over effort.
Yeah, it's not load over effort. It's effort arm over load arm. So in an ideal lever system, please note it because there are two different things. Mechanical advantage formula normally is MA equals to load over effort. While the mechanical advantage in an ideal lever system is effort arm over load arm. Thank you.
Okay, sir.
Yeah, thank you, Mr. Femi. So I want to say yes. He said, "Well done, sir. Thanks for the lifelong teaching of physics and make it easily relatable subjects as against the abstract knowledge we knew in time past." Thank you for your concern. Thank you for the advice. Thank you so much. A call, please call me. Hello.
Hello, sir. It's Blessing.
Oh, Blessing again. Okay. Still want to participate?
Yes.
Yeah. Okay. So what is efficiency now? What is efficiency now?
Efficiency is the rate at which a machine works.
Okay. That's how best you can define it.
Yes.
Okay. So can you give me that when a machine has a mechanical ratio of 4 and velocity ratio of 5, what is the efficiency? Hello?
Sir?
Blessing. Calculate the efficiency of a machine which has mechanical advantage of 4 and velocity ratio of 5.
100.
No. You should remember that there is no machine of perpetual motion. There's no perpetual motion machine. No machine has 100% efficiency. You should calculate straight that efficiency is mechanical advantage over velocity ratio times 100. So yeah, calculate now. Mechanical advantage over velocity ratio times 100. Please, do that. And I gave you that the mechanical advantage is 4. Velocity ratio is 5. Yeah. Blessing.
Sir?
Are you there? Put your mechanical advantage of 4 over. Put it top. Put velocity ratio, which is 5, down. Then multiply it by 100. Give me the answer now. Hello, Blessing.
0.
No, it's not 0. Okay, 0 what?
0. 1 point.
No. You don't get that. That's too bad. Okay? That's too bad. That's 4 over 5 times 20 times 100. That's if you use 5 to cut 100, it will give you 20. Multiply 20 by 4 to give you 80. That's 80%. The efficiency is 80%. Okay? The efficiency is 80%. Thank you for your attention. Thank you for being there always. Thank you. So we're reading up now because the class is closing up because of time. And I want to say a big thank you to all listeners, students, parents, our teachers at home, because there are teachers who teach us too. They're still at home, and lovers of knowledge too. So we've been able to go over and over subjects that is basically efficiency of machines. And I want to thank you for your time. I thank my studio producer, Mr. Debbie. I call him Sky Power. I want to thank the station manager, Mrs. Tokumbo Ishola. My producer too. I thank you, Mr. Femi Ogunyejo. Until we meet again next week, I remain your host, Kenny BADMUS. Thank you for being there. Thank you for your time. Bye-bye.